An event is right now going on in between 90 and 100 cities. And hopefully we will have the best innovative ID. So, first I will talk a little bit about the program for these 2 days. Today and now this morning we will have two very interesting presentations. Sandahl from Ericsson will talk about how to make a prototype, which I think is a very good idea for the competition that lasts for about 24-40 hours. And will also hopefully be very good to know later on. And we'll also have a very interesting presentation from Patrik, who was writing his thesis for NASA. But so before we start, make sure everyone that you register on the website, and then also we also have to create a web page or a project page on the web. And in order to win this competition, which will be a trip to NASA to see when the rocket takes off, you will also have to make a video. But I think they can make a video later.
Yep. Until Thursday evening.
And the winner will be picked out of a jury. And also you can elect a winner. We have a box there that will be used tomorrow after the presentation. So at 1 o'clock tomorrow, everyone will have a project presentation where you can say what you have done and hopefully what you will do with the project after this competition. So, what else do we have to say? We have some videos to show, some inspirational videos I hope that NASA have made, and some greetings from some astronauts. Perhaps you should see one of these.
Greetings from the International Space Station. I'm Expedition 39 Commander Koichi Wakata. I want to welcome you to the 3rd Annual International Space Apps Challenge. Many nations have worked to create this magnificent orbiting laboratory that we live and work in every day. Right now, you are collaborating around the world to develop solutions that could contribute to future space exploration missions and to help improve life on Earth.
Innovative thinking sparks huge advances in human spaceflight. We're so excited about all the work you are doing at the International Space Apps Challenge.
So keep working hard to help us build our future. We need you to help us see our world differently.
Yeah, you get some inspiration. We have a few words from Deborah Diaz as well.
Thanks so much for joining us. Now let's get started.
Yeah.
Hello. Thanks for joining us this weekend on Earth and in Space. We're really excited about what's going to happen over the next 48 hours. NASA has a long history of exploring new frontiers in science and technology, and it's been our long-standing goal to involve the world in our discoveries and our exploration. Every year, technology makes it possible for the world to make discoveries together in ways that weren't imaginable 10 years ago. Today, we aim to take full advantage of our globally connected cultures and modern information technologies to create, explore, and solve global challenges together. Thanks so much for joining us. Now let's get started.
Yeah, so here you can see the different challenges as well. I don't know if you've seen all the challenges. Did you have a look at it? And pick one. You could have started to work on it like weeks ago. So I think you should take a look at the challenges and at least and see what's interesting to you. They want us to show the different categories. Yeah, everybody has that link to the official webpage, right? So here you have different categories. You have technology in space, human spaceflight, asteroids, Earthwatch, and robotics. Which one do you think we should take first? Asteroids. Yeah, so every category has its own video as well. Yeah, so 3 of the challenges, they are by the Kennedy Space Center, and they have a special prize ceremony as well, where you can win and you can go to a launch. I think we can
during that time. But my name is Callie Burke. I'm here from Kennedy Space Center, and we're going in that time. But my name is Callie Burke. I'm here from Kennedy Space Center, and I'm the lead for the Space Apps Challenge team here at Kennedy. And so of the 45 challenges that are going to be coming up this weekend for the Space Apps Challenge, April 12th through 13th, we have 3 of them. And so we're going to have experts from each of them going to be talking about those different challenges. So they're going to introduce themselves and the challenges, and then we'll be going to questions. So we'll go first to to the space wearables.
Hi everyone, I'm Jim Miranda. I'm the challenger for the Space Wearables Challenge. I'm here with Luke Kindred and Brad Hill. And so what our challenge is about is developing space wearables for both use in space for astronauts and also here at Kennedy Space Center for ground operations technicians. So we look forward to seeing what cool ideas you guys come up with, and hopefully we can apply that here in the future at Kennedy Space Center.
Okay, and next we'll go to, also we're going to have, we have an additional party who's joining us for space wearables. So Andy?
Hi there. So I'm Andy Allen, and former astronaut, flew 3 space shuttle flights as a pilot and a commander, and currently working on a contract here at Kennedy Space Center.
All right, well, thank you for joining us.
You're welcome.
And we'll go to Ray Wheeler.
Hi, my name is Ray Wheeler. I'm a plant physiologist, and I work at Kennedy Space Center in Florida. And the challenge this year is somewhat related to a challenge we had last year through Kennedy Space Center, and it's entitled Growth Food from the Martian Table. For any of those that might have participated last year, we had a challenge related to deployable greenhouse systems for space. And so this year's challenge will be to extend that, and a lot of the ideas that great ideas that came from last year, but think more about how we might connect food production systems with human habitats. What are some of the issues that we need to consider in doing that? And like the other teams, I'm very anxious for the great ideas that can come out of this whole effort. So I'm happy to be participating again this year.
Thanks, Ray, for continuing to support us. All right, so Phil and Jim, if you guys want to introduce yourselves and the challenge.
Hi, I'm Dr. Phil Metzger, and I'm Jim Mantovani. We're both physicists. We work in the Granular Mechanics and Regolith Operations Lab here at the Kennedy Space Center, and we're supporting a challenge this year for prospecting asteroids, asteroid prospector. And the idea is to have a game that will hop from asteroid to asteroid throughout the solar system, prospecting for resources in order to continue the journey as you go. And the reason that we're interested in this, the motivation for this challenge, is because the asteroids in our solar system are, on the one hand, a great threat to planet Earth, but on the other hand, they're a great opportunity for planet Earth. And so we think by mining the asteroids, we can at the same time set up planetary defense and get a win-win situation where we're bringing in billions of times greater potential resources for humanity, as well as making our place safe here in the solar system. And so the idea of the game is to get more people interested in asteroid mining and to look at strategies for hopping through the solar system to different asteroids.
All right, thank you guys very much for joining us. So, and another reminder is that these are all challenges. So anyone who attempts one of these 3 challenges over the weekend and does a project, and even if you're not nominated for global judging, as long as you complete the 30-second video and include that with your summary and all your resources on your project page, you'll be eligible for a launch viewing opportunity prize. And so each challenge will have a winner, and so they'll have 2 team members who will be able to be invited to come to Kennedy Space Center for a launch, and they'll each have 1 guest. And so last year we actually had people come for the Maven launch, and they joined the global winners, both the winners of the Kennedy Space Center challenges and the Space Apps global winners. So we're looking forward to having that again and seeing all you guys' great projects. So, all right, we'll go ahead and get started. And our first question will be for Andy.
So, do you want to see the questions and answers? It could be a long time. I guess you can go to the Google Plus page and look at it yourself if you're interested. And it's Space Apps KSC. Yeah, so
Should you go on to the other presentations?
I think so.
First, just remember to register and to take some Coke or coffee if you like that. And also during this weekend you can be on the second floor if you want to get more quiet later. And also don't forget that 6:30 tonight, this evening, we will have a NASA hangout where all the cities competing in this event will join together, and there will be some live streaming where you could ask questions to astronauts. That's the next thing.
Yeah, so
Right.
Hi everybody. Oh, I'm writing this. There we go. My name is Martin Törnros. I've been studying Master of Science in Media Technology at Linköping University at campus Norrköping. And that course has a great focus on computer graphics and interaction design, and also scientific visualization, which is why that course been sending or keep sending students to NASA and American Museum of Natural History in New York. So we've had several students throughout the years going to the museum, and I was the first one to go to NASA in this new project that I'm going to tell you about. So about a year and a half ago, I got the offer to go to America, to Washington, D.C., and do my thesis work. So I'm going to tell you a little bit about the collaboration and a little bit about my thesis specifically. And I don't know all you guys' background, but I'm going to keep it. I'm going to do some technical, like dive into some technical details, but I'm going to keep it on quite a simple level. And since we're few enough in here, you can think of questions and you can ask me later, or if you really think I'm diving into something weird, you can raise your hand and I'll just take the question on spot, like right now. Okay, so you can keep your hand up all the time. All right, so I'm gonna assume that you do have some mathematical background and perhaps some programming background. It doesn't really matter if you don't, but I assume you do since you're here. And yeah, I'm gonna try to give you all the necessary background needed to follow me. So the focus on the project that's been called Open Space is about space weather. So it's a collaboration between Linköping University and specifically the Media Technology course, NASA and NASA Goddard Space Flight Center in Maryland, and American Museum of Natural History. And space weather, that is like a broad concept that it contains different parts. So you got the solar wind, which is a continuous release of charged particles that's being released from the sun. And since the sun is rotating, you get this characteristic spiral, which we will see throughout this presentation. And we're also talking about solar storms or coronal mass ejections, which is what we see here on this image. So they are enormous flares of charged particles that form like clouds of plasma that being erupted from the sun. And they propagate throughout space and become ridiculously big, like many times larger than the sun. And they can erupt almost in any direction, and they're really hard to predict. So, and if they, yeah. Much larger than the sun. Since, yeah, we will see. Look at the images later. Yeah. So yeah. So these solar eruptions, they can like erupt in any direction, and they're hard to like to predict. So they might very well hit Earth or any of our satellites, and they're not dangerous to life on Earth itself. But since they are charged particles, they do affect our technology. So we need to be prepared whenever these storms might hit us. And also, if they hit a satellite, we need to be prepared for that. Maybe shut down the technology, or the satellite might break down to an irreparable state. So it's yeah, really necessary to know when this is going to happen. So what NASA does is that they have 3 satellites. They have 2 satellites called Stereo A and Stereo B that orbit around the sun in almost the same orbit as Earth. So one is ahead of Earth and one is behind Earth. And you see them here in the top left and top right corner where you see the dates. That's where the satellites well, right now the satellites are almost behind Sun, seen from Earth's perspective. So they keep eyes on the Sun all the time, together with another satellite called SOHO, which is positioned between Earth and Sun. So these three satellites always face Sun, and we can always see what's going on Sun's surface. So whenever there is an eruption, we can measure the speed of this solar storm. We can measure, we can measure how big it is at eruption time, and then they use this data as input for a simulation. So then they simulate how this cloud or plasma is going to propagate through space throughout a couple of days and see what it might hit on its way. Because we can't really measure the plasma cloud while it's actually propagating. We can only run a simulation from the initial state. So my work, I was at Goddard Space Flight Center, which is one of the campuses of NASA. It's located right outside Washington, D.C., in Maryland. And this is their main lab. You see this girl here, Layla Mays, wonderful person. She's one of the people on Earth that knows most about the Sun. Really fantastic scientist. The three images we see here, they are real-time data of the Sun. So every morning we were a group of about 20 people. We met in this room, and we had a morning meeting looking at what the Sun had been up to for the last 24 hours and discussing what was going on. Made some plots, made some graphs, and discussed if we need to do any needed to do any alerts or anything. And this plot here is one of the NASA's main visualization tools for visualizing space weather. So what we see here in the middle of this graph is Sun, and the green spiral is the solar wind that we're talking about. So that's a spiral of charged particles. And Earth in this image is the yellow dot to the right of the Sun. And that distance between Sun and Earth is called AU, astronomical unit. You might, depending on what challenge you choose, you might come across these different units and different terminology. So, yeah, you might want to figure out what they all mean. So this plot, it's a 2D plot, two-dimensional plot, and it's colored with a rainbow color scale, which is not a good choice for scientific visualization. It's very, very bad for many reasons. And the data they're using, it's three-dimensional and it's also time-dependent. So by showing the visualization on this plot, which is very non-interactive, NASA has immediately lost 2 out of 4 dimensions. So they kind of lost half of their data. And on top of that, they're showing it in a very, very bad graph, actually. And I guess it's also supposed to be circular, but it's more oval. So yeah, they're really good at what they're doing, like scientifically and doing research, but presenting their data and visualizing it, they're actually not that good. Which is why they want us from Linköping University, because we're actually much better than on that, which is fun. So my work, my thesis was to take this data and make better visualizations of it. And I'm gonna do some introduction to some 3D graphics here. Do any of you know any computer graphics? Yeah. Well, that's good. So what I was gonna do, I was gonna take this NASA's data and visualize it in 3 dimensions. I was not going to look at the time dimension in my thesis, but the next person who followed me, he was looking at that dimension. So I'm going to look at one time step at a time. And what I did, I took all this data and I put the data in a 3-dimensional grid. So those of you who have been working with computer graphics, when you work at it in an introductory course or such, you usually work with 3D meshes, which is polygon data. So you have triangles, and that's how you visualize your 3-dimensional data. This is not what we're doing here. Instead of using polygons, we're defining a 3-dimensional grid So you can think of pixels on a computer screen or your television, but here we're instead talking about voxels. So instead of talking about a two-dimensional grid with pixels, we're talking about a three-dimensional grid where each cell is called a voxel. And each of these voxels has a value, so it can be a physical value, such as pressure or temperature or any physical value. It could also be a vector if we're visualizing a velocity field or something like that. So all these cells or voxels, they map to a value. And what we do when we render these images is that we take, for every pixel on our screen here, we shoot a ray through the screen and through our volume of data. And we sample, along this ray in the volume, we sample all these data points. And we map each value to a color. And then we accumulate all these colors. And they finally make up the colors on the screen. And we do that for every pixel, so we have our final rendering. And the good thing about this compared to polygon rendering is that we take the whole volume into account. We don't only take the surface into account. We get a really nice nice visual representation of the full volume. So short introduction to volumetric graphic. This is a huge research area and ongoing. So this is applicable to so many different fields. So before I started working, I took a little unofficial guided tour. Actually snuck into some of the buildings next to mine. This building right here was the house next to my office. This is where they test all the satellites before they're launched into space. So they have these chambers of like where they can go from extreme cold to extreme heat in extremely short time. So they're simulating actual scenarios that these satellites will face once they're out in space. So everything they shoot out goes through this process. This is the very spot where they once built the Hubble telescope, and right now busy building a newer, better one. This is a piece of space blanket. That's the official name. And they wrap that around every satellite that they shoot up in space. So it's kind of like insulation for satellites. But since there's no atmosphere up there, they work quite differently. But it's the same concept. There are some other engineers busy building something. Yeah, so it felt quite good to be at Goddard. So I started getting to work. This is one of the early renderings of my work. I was using a volumetric rendering engine that's being developed at the Visualization Center in Norrköping, where you can load data, volumetric data, and you can define transfer functions. And a transfer function is it's like a histogram where you map values to colors. So this little graph that you draw, that's how you define how the rendering is going to come out from the data. So how you map data to color. So this was maybe after 1-2 weeks at NASA, and I was of course super proud and super happy. I come to NASA and I immediately have a good result to show them, and I'm like, yeah, I'm done with my thesis. I can go road tripping. So another rendering, which looks a little bit more like their 2D plot. So I show this at one of the morning meetings, and everyone got really quiet. I'm like, yeah, cool. There you go. They're so impressed. Until someone says like, yeah, they look very good, but they're not so scientific. Our data doesn't look like this. And since I'm not used to the data, I didn't know what it was supposed to look like. I just assumed this was scientific enough. And the thing they pointed out is that it's way too symmetric. So what I did here was actually not visualizing this full sphere of data. I actually had just an eighth of a sphere that was mirrored along all the axes. Which you can see that like the blue part here is actually mirrored. So this was not that good, and I couldn't really point out what I did wrong. I thought my code was correct, and I looked through it many times. So yeah, I discussed it with the scientists at NASA, and they gave me a new data set, and then it all of a sudden looked like this. So yeah, I came really proud first, presented my work, and then they took me back down on Earth and gave me a new data set, and yeah, it turned out actually that NASA had given me a invalid or distorted data set, and was actually nothing wrong with my code. So then I grew a little bit again and realized that, yeah, this is pretty cool. I can actually point out bad stuff or like distorted data sets for NASA. They hadn't even noticed that themselves. Yeah. Yeah, maybe they will do that for you as well. So if you find something something bad, maybe that's the case. Yeah, I don't think they did that, but who knows? So here's another rendering of the same dataset, where you can see the 3D structure a little bit more. So the blue spiral here is the solar wind, and the yellow-orange part is the solar storm. And you can also see like a spiral shape in the center, which is which would not be considered the solar storm, but would be considered part of the solar wind. So it was quite hard to define like one single transfer function that would separate the wind from the storm, which is what we wanted to do. And I think in this rendering we're visualizing pressure. So this is plasma pressure or plasma density. And you can also see in the storm, the cloud, that it kind of looks hollow or transparent in some parts, and it kind of looks like it has holes in it. And the scientists don't believe that this is the case. So we had to look a bit further at the actual representation of the storm. But the wind, we were quite satisfied with. So instead of just visualizing one single variable to represent both the wind and the storm, we started separating them. And we took one variable for the wind, and then we actually ran 2 simulations of the storm and subtracted them from each other to get this smooth cloud, which is more, which would be like a better representation of the storm. Out of a scientific perspective, it's probably not the best representation to use like 2 different variables in the same plot, and also to run 2 different simulations and subtract them. That wouldn't be considered super scientific. But in this particular case, we were making renderings for the American Museum of Natural History, which wanted to make a big dome presentation about these events, and then we also needed visually pleasing results that still are scientific, but they didn't need to be like bulletproof scientific in that very case. So these images turn out to be much nicer. And what I was working with at the end of the project is what we choose to call volumetric rendering in spherical coordinates, which was a new concept that we developed and implemented. So traditional volumetric rendering or raycasting, as I described it before, is that you take models and you put it in a 3-dimensional grid, and this grid is usually defined in Cartesian coordinates. So you got x, y, and z, which are orthogonal axes. And if you have a low-resolution model, then you might end up with these visual artifacts that you can actually see the discrete voxels. And that's not very good. That's not what you're after. And since the data we were working with is defined in spherical coordinates, we got the sun in origo, and then you got a sphere outside of that. That's how the data is defined. And we thought like it's ridiculous that we should like transform this model into Cartesian coordinates. We should just instead of transforming this model to Cartesian, we should just take all these rays and transform them into the model space. So instead of doing all the interpolation in X, Y, and Z, we did them in radius, latitude, and longitude, the spherical axis. And without adding any extra voxels, without adding any extra information, still keeping the same very low resolution model, we got this middle render. And you can see that we see no discrete voxels. It's very, very smooth. And there's no extra data at all. And this was a completely new concept. We read different articles and like thought to ourselves, like someone must have been doing this before, but we didn't find anything. Still, you see some artifacts here. I don't know how visible it is to you on this projector, but you see that there are some like lines that we don't really didn't really like. So what we did in the last rendering is that, again, without adding any extra information or adding any extra voxels, still super low resolution, we doubled the amount of voxels in the radial axis, but we halved, or we cut the amount of voxels in the latitude axis in half. So we just restructured the voxels, but we didn't add any. And then we got rid of all those artifacts as well. Yeah, I was doing that for a few weeks in the end, and it started out as just like this idea in my head that we should be able to do this, and it turned out that it was very good. And I mean, you can always be playful with the data. So also in your projects or your challenges that you're getting now, you might like get on a visualization task, but don't just go for the first like visualization that comes into your head. See if you can like come up with something new, because that's what's gonna like impress people. So by the end of this project, I got the honor to go to San Francisco and represent NASA for this specific project. So here's me with a Puerto Rican colleague, and I had a big poster. So this is the biggest geography and space fair in the world. So about 20,000 visitors came. And this is an ongoing work. So here's the same lab that I showed you in the beginning. This is the full staff of the CCMC lab. These are the people that work with visualization and making all this data open to the public. So most of the data that I was working with, you can just download from the webpage. And NASA has this big program right now that they want to make as much data as possible open to the public. So there's so much to get hold of. Might not be the easiest thing to web page to navigate through, but once you find out where to get the data, there's so much to download. So these are the staff members that I work with, apart from two guys here in the middle. These are actually also students from the media technology program that arrived in Washington maybe a month ago, and they are the third and fourth people to go there. I was the first one, and then there was another guy after me that was looking at animating this whole sequence, and I don't really know what their tasks are. It's just started. But NASA is super happy to have this collaboration with us, and they keep asking us for more students, and first we went one by one. Now they're asked for 2 people, which must mean that we're doing a good job. And they've actually been using a lot of the renderings that me and Victor, the guy that followed me, a lot of our renderings when they've had official meetings with NASA headquarters to get fundings, and with the National Physicist Association to get fundings from them. So yeah, our renderings have really come into use at NASA. So yeah, super happy to have been there and see what they've been doing and actually helping them out, and also getting a lot of good insight myself. Right. I'm still working with the people that are in this project a little bit at the Visualization Center in Norrköping, but I'm running my own my own business. But I'm a consultant, so I'm right now working a lot with interaction design in the medical field. So developing prototypes for pathologists to introduce new technology to them. Yeah. So I'm not really in the space business anymore, but I keep in good touch with the people that are, and I mean, I might get dragged into it. Yeah. Mm-hmm. Who, sorry? Actually, I don't keep very good track of them, so I really don't know. I know that the structural design is a very frequent visitor and collaborator with visualization center and nothing. He's part of the USP, but yeah, no, I'm sorry, I don't keep up to date. So I wouldn't know. More questions? Okay, you can ask me. Yeah.
From what you learned from NASA, what can you apply to your business?
The main thing I learned, I worked a lot of the actual implementation. I worked a lot by myself, like using a lot of the stuff I had learned at university. What I really learned at NASA was how to work and collaborate, like cross-disciplinary. So I was working with like these people here. These are crazy scientists. Like these are people are so good like at the physics and math and chemistry and everything, which I know enough to like understand fractions of what they're saying. Like I can follow them if they really explain it on my level, but I wouldn't know what they were talking about like if they were just talking internally. So just being able to collaborate and actually make useful things out of data that comes from a field that you really don't know anything about. That's the main thing I learned. Just to practice understanding like people's problems that are not from your background. Yeah, both things actually. So visualization, it's a tool that is like visualization is a tool that helps like take really like advanced or complex data and make it useful and understandable for people that might not be used to the data. Like, I mean, experts, they would be able to just look at any graph and they would be able to tell what was going on. But the reason they wanted these images or these renderings is that they, like partly for the scientists, but mainly for the museum in New York, the American Museum of Natural History, to be able to use all these renderings, to use accurate scientific renderings in like a real-time spaceship. So they wanted to like be able to be in the dome theater and like have a presentation of space or sun. And all of a sudden, NASA discovers that a cloud of plasma is coming to you, and then they would be able to like sit in dome theater and be able just to squeeze that into the presentation. Like, oh, right now we're realizing that something is hitting us. So that's why we want these visualizations. So part of my challenge was to understand what these scientists were talking about and put it on my level, like in my head, and then pass that on to the next person who maybe knew like even less about it. So yeah, both things. Yeah. 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 Uh, yeah, it's a very good question. So, one of your middle questions was, is it limited by the satellite? No, it's definitely not, because the satellite, as I said, we're just getting input data from, we're taking, like the satellites are taking photos of the sun. So we get still shots, and we see that, okay, or we get several still shots, like a series of shots. And we are able to tell, okay, it's this cloud is going to have this velocity, and it's going to have this angle, and it's going to be this big, and whatever parameters they have. And then they use this data as input for a simulation. And they can run that simulation in any resolution. So the limitations of the satellite, they're not limitations for the resolution at all. So we can get super, and these are, like, the original data is super high resolution. To answer your actual question, is that, like, I chose like quite small grid here to present the concept of spherical raycasting, to make this artifact like extra visible. We would probably in the end work with a grid that is about 256 in each axis, and restruct the data, as I said, like in the third rendering here. But the problem is that I've been looking at one time step at a time. So I've been loading all this data onto the graphics card, but this data that we get from the simulation is not one time step. It can be like 1,000 time steps. And if you load, so say we have 256 time steps, that means that we have 64 times as many voxels for each time step. So it's by the power of 3. So the amount of voxel increases ridiculously fast if you increase the volume. And then maybe we're supposed to, like, run the full animation, and we're supposed to load all this data onto the graphics card, preferably in real time. And that's not going to happen, especially not if you run this simulation of the solar wind together with another simulation of Earth's magnetosphere, and then you have load all this other data of, like, all the stars that we know, because we want to put this together in, like, a complete show. So it's virtually impossible now, like, with the technology that we have, to load all this data onto the graphics card. So that's actually the guy that came after me. He was looking at how do we represent, like, the time dimension in this. So he was using a lot of, like, different octaves, like tree structures, to make a good pipeline for actually rendering the time. But yeah. Yep. Okay. Thank you.
Yeah, that was a great presentation.
Thanks.
Makes you want to get on hacking. Yeah, should we take here? That's it.
Yes, I have to wait for some wait of this one. This is actually one of the things that differentiates between prototypes and products. Usually don't need to have support for updating and such in your prototypes. Oh, while waiting. Good morning, guys. I'm Patrik Sandahl. I'm work with software development at a big telecommunications company called Ericsson, located just a couple of 100 meters in that direction. I strongly believe in working with prototypes in all phases of the development process. Great. Can get it as full screen. Great, fantastic. So I will try to answer a few questions about how to make prototypes and what is a prototype and why to make prototypes. Do anyone know the origin of the word prototype? From Greece, yes, of course. Very much of all words have a Greek origin. It's actually two words, protos and typos, and in some simple translation is the first form, some kind of early template in how to make a product, something in between an idea and the final product. And to be more concrete, what is it not? This is Swedish for you English-speaking people, but I think it's quite clear anyway. It says that the prototype is not the product. I mean, when making products, you have to take so many considerations. You have to maintain maybe a long life cycle. For instance, when we make our communications equipments, exchanges and network equipment, we have life cycles of many years that we need to get new requirements, need to implement, and we need to support. We need to support, for instance, upgrading. It may be that we have to consider legal regulations, or if we think about user equipment like smartphones or application for smartphones, we have a broad variety of users that we need to make sure that it's simple to use and so on. But with prototypes, we are much more narrow. We have only one thing that we really want to show or prove with our prototype. We have a very short life cycle and a limited amount of users, and it can be you, which is the user for your prototype. And with that, we can also say that making prototypes is different compared to making products. If we're gonna make a prototype, we have this one thing that we will show or we will prove. Then we can cheat as much as we like for all the aspects or the considerations that we don't need to take care of. We can, so to say, we can play God as long as we clearly show what the purpose of our prototype. Well, usually when I do prototypes, or when I am involved in prototyping, there are usually 3 different kind of prototypes that we are doing, and so we can think of that we have a great idea. We would like to make an application that where the user can handle the application on a smartphone. We will have a server system that collects a lot of data. It could be internet data, like we connect something from Twitter, or we can have a big sensor network from where we collect a lot of sensor information. We would like to do some analysis and number crunching on that data, and we will provide a nice visualization where the user can zoom and so on in all that data. So what kind of prototypes can we do to help us work with that idea in different prototypes on our way to, in the end, a product? One kind of one way to think of prototype is that we have a great idea in our mind. We will have it out from our mind into the real world. And one thing is that, okay, how will this application look for the user? So maybe the first prototype is just the idea that we have in our head. Use a whiteboard or just paper and pen and draw it. Draw the scenarios. How will this application look to the user? How will the user interact with it? How will our visualization look like? And maybe the next step of this kind of prototype is to make a dummy application, which is just static, which does not include any real data. It just has pictures. But you can let the user navigate in the application and see how the menus will look like and how you will zoom into your visualizations. This is one type of prototype which I myself think is very useful with regards to get your idea out of the head and really look like how would it look in a real world scenario. The next thing, this is, I think, kind of prototypes that you work with your visualizations. Actually, now we shall start making the real functionality. We have some data. We know how we would like to present that data in those great visualizations. We need to understand how can we analyze the data, how can we mine data or information out from maybe huge amount of data, and how can we make algorithms that we can visualize it nicely and into an understandable visualization. So we need to work with algorithms. We might use tools like MATLAB or the programming language R, or different kind of visualization visualization frameworks to actually take the real data, number crunch it, and make the visualizations that we like to show. And the third kind of prototyping is how. Now we'll know how how it should look to the user. We know how to algorithmically calculate everything, but how can we make this a real product? How can we ensure the characteristics? How can we get access to the data we need? What kind of APIs are there? For instance, if we would like to get data from Twitter to analyze trends and so on, what does the APIs look like? What kind of frameworks do I need to fetch data from Twitter? How much data will it be? How can I handle the capacity of storage? I maybe have to research a little bit about distributed databases, for instance. How do I ensure that I have capacity to do all these kind of calculations? It will be new data incoming with high bandwidth. How can I calculate all this, for instance, in almost real time? Do I need to have a scalable solution for the number crunching? I may have to investigate and prototype for a scalable solution, a map-reduced solution with frameworks like Hadoop and so on. Really to make sure that you can build a solution which can handle the different characteristics of the application systems that you would like to build. So this, for me, is three basic kinds of prototypes. And so what are you gonna do during this weekend? So it's about to understand what is my idea? What would I like to present? What would I like to prove? What would I like to show? Is this the kind of user experience? Maybe then I should start just with a paper and a pen. Are I provided with some kind of data and I would like to visualize it in some way? Yeah, then maybe start to look how would like an algorithm for visualization of this data look like? What kind of frameworks can help me to rapidly make such a visualization, and so on. So that kind of questions we all the time have to ask ourselves and try to answer ourselves, and then choose the approach how to go on and develop your prototype. So, any questions? Otherwise, I wish you all really good luck. I look forward to see your presentations tomorrow for all your cool projects. And yeah, thank you. Yeah. It depends on what kind of software. So we go back to that. What do you like to show? Is it some interaction software? Yeah. It's a kind of smartphone, or what kind of? Is it a user experience kind of things? Computer based. I think it's I think paper and a pen or a whiteboard is the best engineering tools always been, and I think it's always gonna be the best engineering tools available. And so I think for me the first step to get an idea out from head and try to make it more concrete is paper and pen. But then of course I think get it working with menus and all kind of user experience things, and there I have no recommendation from the top of my head with regards to how to design, but I'm really sure just a few Google questions. Yeah. Yeah. Okay. Yeah. 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 I mean, there are not rules written in stone. I think it's a process for getting things out from your head and moving towards something that it become real. And if you have prototyping tools like this, I think it's excellent. And what's important is that you easily, when you have an idea, you can try it out, and you can think, no, this was not what I wanted to look like, and you easily can try a new approach. And compared to actually, you should write the user experience you programmatically in C# or Java. It takes hours to actually get something up and get menus and get sliders and so on. It should be seconds or minutes from an idea that you can see a concrete result of your idea. Yeah. I believe in that you should actively get feedback, and if you work with the user experience, I think one important aspect of the user experience that it should be usable and it should be intuitive and so on. So go to your friend and say, hey, look at this cool thing. What do you think about that? And your friend is saying, oh, okay, I don't really understand what I should do with this. And then it's a good feedback, and your early feedback, okay, this isn't really what I would like to have with this user experience. So I absolutely collaborate and actively seek feedback. Yeah. Oh.
Thank you so much for this presentation. It was really good.